All right, well, I'm going to go on mute until it's my turn.
Okie doke, me too.
Okay, so it's the top of the hour. Should I start? Hello?
I'm ready.
Okay.
Ready?
Well, I guess if the AMS says we can start, I'd just like to thank everybody who's attending this webinar. It's a continuing series. This is webinar number 3 of 4. And in the continuing study of the evolving role of the human in weather prediction and communication. And this topic is training and proficiency for future forecasting, and Dave Schultz and his colleagues have put together a great presentation looking at what sort of future training and proficiency we'll be needing for humans to stay in the forecast process. And there is a doodle poll coming up, and hold your questions and answers. At the end of this webinar, we'll be doing Q&A, so think of some good questions. And without further delay, I'll hand it off to Dave. Thanks, Dave.
Thanks. And we're going to be joined here in a minute by Harold Brooks, Gary Lackman, and Paul Rober. And what we're going to do is give the various perspectives from our organizations about the topic that Neil's already mentioned. So before we get started, want to know who our audience is. And so here's a poll for you. If you could go to your computer and click which word, which term best represents how you view yourself. Give you a few minutes to do that. Everyone got it? So I'll turn this over to the AMS whenever they see that enough people have signed into the polls and people aren't signing anymore, then they can reveal the answers. So everyone clicked on something? AMS, how we doing?
We got 39 out of 54, so 72%. So.
Okay. Do you want to reveal the
Yeah,
results?
the top is research or management for government or private sector, 33%. Government forecaster is 35%. So government forecaster.
Okay, great. So do we get to see those results, or no? Guess not. Okay, anyway, we'll get started. So as we were talking about what we wanted to discuss in this webinar, we ended up focusing on 3 topics. And the first is training and education for various jobs in the meteorological sector. Gary has made a really good point that students who are entering university this fall will be employed for the next 40 years, and so around 2060. And if you can look back and think about how much progress has been made, you know, from the present back to 1980, you see that all these techniques that are common to us now were not familiar to people who are retiring now when they were entering university. And so that's a pretty big ask to be able to predict that far in the future. And as a university, it's very clear that a university education will not be sufficient to carry one through their career, given how quickly meteorology evolves. This leads us to the second topic that we wanted to talk about today, and that's the tools and techniques that forecasters use, of course, will evolve during this time. What are they, at least as far as we can see into the crystal ball? How will they be used? And the third thing we discussed was communication. Paul points out that a perfect forecast is perfectly useless if A, it's not actionable, B, it is actionable but nobody listens, or C, it is actionable and people listen but they don't understand it because you've failed to communicate it in the context which makes it meaningful to them. So the forecasters of the future will have to hone their communication skills, and we'll talk briefly about that. Finally, we'll offer some thoughts about what the future may actually look like. Before we get too deep into this discussion, we should mention the difference between training and education. Training is what you teach people to do, is what you teach people to do existing well-defined tasks. But education is giving people the skills to develop new techniques, the things that training can't really provide. As 3 of our panel members sit at a university environment, we all strongly believe that our role is primarily education. Of course, there'll be some training elements that we deliver at universities, but the kind of job-specific training that one is likely to receive will be largely the role of employers. So if you have a chance after this webinar and this interests you in particular, take a look at what the AMS statement says for guidance for universities to deliver in order to offer a bachelor's degree in meteorology. And you can do the same thing for what the National Weather Service requirements are for a meteorologist position. When you look at the elements that they want you to take, there's not much space left for someone to have a broader education. They fill up a lot of the credit hours that one would have to take. So are we limiting the flow of people into our organizations, into our meteorological environments, because of the requirements that we're placing on them? This very restrictive idea that you would have to, you know, train everyone to meet these narrow standards. So specifically, yes.
Dave, we had a request that you take it off presenter mode because your notes are visible. Just a brief interruption.
Okay.
I'm sorry.
Let's see. That one.
Oh, beautiful.
Okay.
Thanks, Dave.
No problem. So specifically, let's think about the skill sets for which we are educating students. Let's go back to the point that Gary made about first-year students retiring in 2060. Even before we get to that point, that milestone, another point that we'll want to touch upon in this webinar is the present, what we're doing now. Are our current offerings at universities sufficient to prepare graduating students now? And I'm going to draw in my own university, the University of Manchester. Although we don't prepare weather forecasters per se, we have reorganized our undergraduate curriculum just this past year in Earth, Atmosphere, and Environmental Science to give students more modern computational skills, including numerical methods and formal Python training. Now, one of the biggest challenges that we had to overcome in redesigning our curriculum was, of the 77 academics in our department, only a handful were capable of teaching Python. One was on paternity leave and the other two already had heavy teaching loads. And so this caused us quite a bit of consternation trying to come up with a program with this limited abilities of our present academics. So when we think about meteorologists, we have other skills that we want our students to appreciate and be exposed to, in a traditional meteorological sense. And so the active learning of these new techniques in computer labs, other practical exercises, ensemble forecasting, visualization skills, machine learning, artificial intelligence, it's going to be very hard to upskill a professoriate into these skills. And these are some of the challenges that a university faces. And one of the reasons why it's really, in some respects, up to the students to get the kind of education that they want. So at this point, I'm going to turn the mic over to Harold, and he's going to give us his perspective from the federal government.
Okay, in the United States, tradition, if you go ahead and, traditionally, the federal government has been a major hiring center for graduates of universities in the United States, and there's really two basic kinds of jobs that I'm going to talk about for those. The first is forecasting, and Dave, can you get me back up to that slide? Thanks. Okay, and clearly the job's going to change dramatically through those careers, through that 40-year period. And one of the big things that's going to mean is we need our people to become flexible and to be able to perhaps do a lot of different things, because the job that they do when they're near their retirement is going to be a very, very different job, even if it's technically still the same kind of position. One of the biggest things the National Weather Service has been encouraging, and other and weather services around the world have been encouraging recently, has been decision support. And that involves a whole lot of things that we don't really have thought about traditionally in meteorology. You have to interact a lot with non-meteorologists. We need to understand how people, including forecasters who are making the forecast, actually make decisions with information. And we need to be able to provide information as needed, so that it becomes a more on-demand, or not a particularly timed forecast process, but it's such information that people need. The other thing I think we've realized particularly over the last decade, has been the role of stress on forecasters. Weather forecasting, making decision under uncertainty, under great time pressure, is a source of great stress, and how forecasters handle that, how they deal with it, how they continue to make good decisions in stressful times, and how they cope with those kinds of events is something that we really haven't figured out how to do. And another aspect of forecasting that really needs to change, or that is changing, is the notion of looking for expert teams and not necessarily groups of experts in forecasting. We really are, the idea that a group of people working together as they create a forecast add more to the combination adds more to it than the individuals have, is something that we really need to figure out how those teams are created, how they exist, how we interact with other people as part of the forecasting process to get the most value out of it. This has been studied in some other fields, things like how do you make a really good team in an emergency medicine unit in a hospital, but how do we actually make these kinds of teams on a day-to-day basis in weather forecasting, particularly when via the demands of shift work, we're constantly creating different kinds of teams working together, and even out of a same relatively small group of forecasters, how do we actually make those teams work as well as we possibly can? And if we can move on then to the next big area of forecasting, or of hiring, research. And research within the federal sector is perhaps at times a little different than the research within the academic sector. We're working on the notion particularly, and I think this will become even more true as we go on in time, to improve the value of the forecast, not just the quality of the forecast. How do we make sure that that information, when we talked about, when Dave mentioned the actionable information, how do we actually have information that actually helps people make better decisions and that they find value in the forecast, not just that the forecast look more like the actual weather event. That means we need people who can identify problems, can see what could be improved from the current system, how can we go about that, what can be done as well as what we would like to do, and it's going to require the creation of people we need to have people who are both interdisciplinary and multidisciplinary. So we need to have people who know more than just one narrow field, but also people who can work with people who are experts in other fields. And that, I believe, one of the big things that's going to require for our next generation of researchers is a functional knowledge of non-physical science fields. I don't think that we have to have people who become meteorologists who are experts necessarily in psychology or decision sciences, but they at least need to know enough about those areas to be able to converse with the people who are experts in those fields. And let's let those people provide their years of training and education and experience to provide the best information we possibly can. And this kind of goes back to the same thing as we see as I mentioned in the forecasting, the developing teams of experts, or expert teams rather than teams of experts. The other thing that research, I believe as a role of research, is to be the conscience of the operational sector. Not necessarily what we would really like to be doing, but what we can do, and also what's scientifically rigorous when we do forecasting. So that forecasts are based on our best understanding of how the atmosphere works and our best understanding of how to use the tools that we have available to us. And next slide, please. And all of this in the federal sector currently goes under something called the GS 1340 series, the meteorologist. And the requirements to become a GS 13 meteorologist are listed here. You have to have a degree in the right kinds of things. It specifies some of the meteorology. And I want to say, as an aside, in terms when we start talking about the course requirements, this obviously has an impact on how our partners in the university fields, university systems actually work, is knowing that many of their people will be hired in these kinds of positions, they need to be taking this into account as they design their programs. So you see the list of the meteorology classes: 6 semester hours of physics with at least one course that includes a laboratory session. Why the physics classes, and I say this as an undergraduate physics major, why physics classes are favored for having the laboratory session and not something like chemistry or some other class, or even a meteorology class, is something that I'm not completely sure. You have to have ordinary differential equations and at least 9 hours from this really long laundry list of courses. And they're for a physical science major. And note that all the new stuff that the National Weather Service has been doing with looking at decision support and impact-based warnings and all that involved, in large part, non-meteorological aspects, but none of that is included in this coursework requirement. And I think one of the really also interesting things, if you click one time, this definition is almost 30 years old. There was some minor editorial tweaks to it, but this is essentially the the GS-13 requirements that I had to fit when I entered the federal workforce in 1992. So when we only had a few NextRad radars in, we have the same job description now, even though all of this stuff has happened to change the way that the background for the National Weather Service forecasters and for researchers has gone on. And I think I have one more slide, if I remember right. Yeah. So the GS 1340 describes a really homogeneous workforce in the face of a need for diverse skills. And so all the discussions that I brought up about the need to try to improve the quality of forecasts, the need to provide decision support, essentially the current definition that we have in the federal workforce really is not intended to meet those kinds of needs. And I think this puts a constraint on the universities that the federal sector really needs to work on, and trying to create a group of people that can actually meet the needs that the National Weather Service and the research community that helps support the Weather Service are actually saying they're trying to do. And I believe our next speaker is Gary, if I remember right.
That's right. Thanks, Harold, and thank you all for being here. I'll just try to I'll probably amplify on some of the things that both Harold and Dave have stated. But as an educator, we really have to keep our eye on how the job market is changing and how career trajectories are changing, because we want to make sure that our students have an education that's relevant and up to date and that will help them going forward. This last summer, there was a really interesting workshop held out in Colorado called Mind the Gap, and it was sort of about the possibility of diverging skill sets between what students come out with and what they really need when they go into private sector jobs. And so I think it underscores the point that as educators, we need to keep an eye on where our students are going when they graduate, and a lot of them are going into the private sector. So even though we still want to meet that 1340 requirement and have students that are eligible to go into National Weather Service careers, that's not what most of our students do. And so it's important for people in all the sectors to realize that we have to really provide a broad skill set so that our students are prepared for a real diversity of careers. And that's different than it was, So that these additional emphases, some of them are the same in the government sector or in the private sector in terms of communication and being able to speak to non-specialists and de-jargonize messages. And then also underscore something Dave said, that we're educators, and so it's not just about training and job placement, but the fact that tuition is so expensive and becoming more expensive all the time, parents and students alike, they have to know that they're getting a return on their educational investment. So we do want to make sure that we're preparing students who are marketable and who can compete for good jobs in the field. Next slide, please, Dave. So the communication to non-scientist and non-specialist aspects, we hope that any graduating senior in meteorology could give a useful description, a technical description of a 500 millibar height and vorticity map, and kind of explain how that will affect the weather. But I think one thing that we don't do enough of is to try to put that technical information into an applied context. I know that's something that that Paul Rober does a lot with his connections with a company. But I think one of the things they talked about this summer at this workshop, and Paul Rober, who will speak next, was there as well. It'd be nice to have a set of use cases so that if there was an extreme weather event and the student was describing it in a weather briefing, it'd be great to explain, what are the implications for, different sectors, for the financial sector, for the transportation sector, for the agricultural sector, or what have you, energy sector. I think it's good to get students thinking about those impacts at an earlier stage, and that requires us long in the tooth professors to, reach out and interact with people in the community to find out use cases that we can help get our students thinking about, and that might be another way to help prepare students for the workforce. If you could go to the next slide, please. So, you know, there's always the computing and data analysis aspect. And, you know, for many decades, they've said, oh, you know, Fortran is going away. And, you know, so there's other popular languages. Python is the language du jour, and R. There's a lot of really nice languages out there that are popular and they're growing. But it's important for students to, you know, kind of see inside the black box. If you have an equation like the one shown here, you know, that has to be translated into Fortran. And then ultimately that will produce output in a weather model. And kind of going from the theory and the equations through the coding to the model output and visualization, there's a lot in there. And it's kind of a black box, but if the students and the people that are using model output, for example, are really going to be able to think critically about it, the more they know about that process, including the coding, the better. And it isn't necessarily just numerical forecast models. It could be, you know, artificial intelligence and, you know, just how that processing works. You know, that helps, that would help the scientist to explain to a user how to best use that model output or that forecast or what have you. So it's always a challenge to try to keep up. And like Dave said at the start, you know, if there's a new programming language comes along and the faculty were all taught a different programming language back when they were in school, then they have to try to update their skills so that they can teach the students the latest and greatest. But at the same time, you don't want to just go chasing after the latest fad all the time. But for something like Python, clearly that seems to be here to stay and growing. And so we need to think about how we're teaching and whether we're preparing our students adequately for those kind of programming applications. But also there's, I mentioned critical thinking here. You know, how do you recognize bad data or suspect information? That also requires a lot of technical proficiency. And then thinking about mobile devices, for example, you know, a lot of people get weather information through their phones. And so I think the more familiar our students are with how to transmit and communicate weather information through mobile devices, the better. And, you know, data visualization is also, I think, really important, especially for ensembles and large data sets. And next slide, please. I think this is my last one. You know, speaking of ensembles and probabilistic forecasts, you know, not all of the end users are used to working with ensemble forecasts or probabilistic information. But I think that certainly, there's a lot of advantages to it, because that way you can provide information about uncertainty, and that's really a key element in any forecasting exercise. But that also probably requires more of a background in probability and statistics. And that might be something to emphasize in undergraduate curricula. And I think there's just a lot of opportunities also for looking at things like extreme value theory and extreme events. The more background in statistics and kind of probabilistic data visualization, the better. So I think there's opportunities there for people that are clever and creative. And I put this graphic here from Professor Brian Tang at SUNY Albany, because it's a really nice way to visualize, you know, the hurricane spaghetti plot. It's kind of more of a heat map. And, you know, it's straightforward, but I find myself, I would more apt to look at that kind of a forecast than just the plain old spaghetti where the tracks are going all over the place. And so I think there's a lot of opportunities, and this is just one example. And so with that, I think I'll finish up and hand it over to Paul.
Thanks, Gary. So I'd like to start to just talk a little bit about some of the new tools that have been alluded to by the prior speakers. And one way to think about this is to think about atmospheric sciences and big data. And in many respects, we're kind of the origin point of big data and data science. We've been working with large model and observational data sets for years, and they're just getting larger all the time. And we've been trying to make sense out of that using various approaches, including both mathematical, statistical approaches and visualization techniques. We have long used one form of data post-processing, which is multiple linear regression, or as we know it, MOS, model output statistics. But there are many newer forms now. Atmospheric sciences has been fairly slow to adopt these kinds of forms. That is rapidly changing now, but as we've been talking about, the formal training for this kind of work is limited in most atmospheric science programs. I'm just showing some of the several examples of ways to do this, and if you check the recent research literature, both in weather and forecasting and monthly weather view, you'll see various examples of this. Each of these approaches has their own benefits and also limitations. And so applying these techniques requires that you be aware of what they are. It's not just a black box, just in the same way that statistics to be used properly is not really a black box. You have to know what you're doing. But all of them share one common characteristic, and they share it with multiple linear regression or MOS also, which is really, it's just a mapping of inputs to some desired output. Typically, the desired output is some forecast quantity that we want to know about. And it may not be directly produced by the model or the observational data set that we're using. Or if it is produced, there may be ways of getting more value out of the data that we do have by doing this kind of post-processing. One of the advantages of these newer techniques, like on the left, the artificial neural networks, what we're seeing there is what's called a multi-layer perceptron, which is basically a series of layers starting with the data that you're feeding into the system, your inputs, through a series of highly connected nodes that use nonlinear transference of the data through these connections to the desired output. That's one example. What's important about these kinds of approaches is that they are nonlinear and that allow sort of complex patterns in the data to be accessed in ways that a linear approach can't do. And that makes them quite powerful. There are also issues with overfitting. So for example, random forests is really just an ensemble of decision trees. And decision trees have been used in weather forecasting for many years. And what we know about decision trees is they tend to be very prone to overfitting of the data, meaning if you have a training data set, you can get a very good result from that, but then when you try to apply it to some independent data set, the performance degrades substantially. And so random forest is basically producing an ensemble of these decision trees, and so it kind of smooths out that overfitting and you get a much better result. And that's just one way of doing it. There's another type of approach which is quite different, which is basically using the principles of evolution, using various kinds of structures to actually produce outputs from the inputs. I won't go into the details here, but it just shows you the kind of variety of approaches that you can use. And really, I think the most important point I want to make here is that it's important in our field to become more familiar with these techniques because they are becoming more common. And again, it's not just a black box. It's useful to know what the abilities of these systems are, but also what their limitations are. And often if you're comparing multiple forms, so let's say comparing a model output statistics piece of information against an artificial neural network piece of information against an evolutionary programming piece of information, you'll find that they sometimes agree quite consistently with each other, but there may also be significant diversity, and that diversity can tell you something about the predictability in a particular situation. Next slide, please. So one of the questions that comes up quite often in these conversations, especially when talking about machine learning, is that given these kinds of advances and the power that they do show and the possibilities that presents for automation, how do we keep humans in the loop? And really, that sort of begs the question, do we even want to keep humans in the loop? I argue very strongly that we do, and I'll explain how. So I've sort of put up a little Venn diagram here. On the left is what might be considered sort of the traditional academic programming, and mostly what research is focused on is very theoretically based. And then on the right-hand side in the blue circle, you have more what's in operations, traditional practice. And if you go too far on the right, and so you're away from the overlap, what you see are the road forecasters. That's also true of the algorithms in machine learning. They really have no context. They don't understand anything about a weather forecast or weather for that matter. And as Harold and others have talked about, context is critically important to making value out of forecasting. And so Chuck Doswell used to talk and write about the scientific forecasting process. And that's really where you're using these kinds of guidance tools in various forms, whether it's multiple linear regression or a more advanced technique, to provide you some guidance, but you're interrogating that information using the scientific process to get the best possible result. And secondly, aside from just producing better forecasts, the other issue that has been touched upon here is weather decision support element. Quite often the people that you're communicating to are not experts in weather. They want this information either from a public safety standpoint, they may be emergency managers, or they want to know about it because they're making some decision which is critically dependent on the weather. They don't want to become experts in weather. They want to know how this weather information is actually going to affect their decision. And so communicating that information is really where the value is extracted from the forecast itself. And I think that's the end of my part.
Right. So what opportunities and challenges will these trends that we've been talking about offer for the training and proficiency that we want in meteorology? We've already seen eye tracking research at NSSL that leads to how forecasters are learning and using information, data that's in front of them when they make their forecasts. So we can expand that and say, well, how can surveillance and face recognition technologies and other technologies that we can't even envision yet, how can these be used in training, research, and education in the future? We can imagine the utility of drones and autonomous vehicles in improving observations of weather systems now, but how will forecasters use this information? A perennial question. Could they be the ones that send out targeted requests for supplemental observations in data gaps or areas of large forecast uncertainty? And how would they know how to do that best? These are obviously places where these kinds of questions need to be explored in the future. And then how will advances in personal computing and computational techniques that Paul has just talked about and mobile technologies like Gary talked about, how will these change the way we distribute and communicate forecasts? Will that change what we need to teach our students in order to make them more modern weather forecasters? So to summarize, we know that graduates from atmospheric science programs have a much greater choice in careers than they did just 10 or 15 years ago. And that's good for our community. It's good for society. Universities must adapt by still providing a base of fundamental knowledge that we expect someone with a meteorology degree to have, but we also need to allow enough breadth so that we can welcome people from other disciplines and even teach a broader range of choices than the traditional options that Harold showed us, for instance, for the federal meteorologist position. So as people in universities, we need to think about how we design curricula in the future, because designing it for employment in the Weather Service and that alone as part of our degree program is no longer an option. You would not have a very, be hopeful to sustain that for a long period of time. It's just not enough need for traditional meteorologist positions. So maybe the next iteration of the AMS statement or the NWS requirements of what a meteorology degree needs to have, maybe we need to rethink what those lists of requirements are and have a community discussion around that. But it's not just the universities and the employers that need to think about this too. It's students. And hopefully there's a number of students out there. You need to think about how you want to be trained to enter the job market. What kind of skills will give you better employability, more flexibility in your careers, both for entering the career market, but also in the long term. So, there we go into this 40-year period again. How do you predict where the community is going to go, how society will change, and how you're going to be adapted to that? So it's not just about the courses that you're going to take at university. It's about your personality, your drive, your career ambitions. You'll need to be more adaptive. You'll have to take a lot of onus on yourself to learn on your own. And you have to take your own initiatives to prepare for these diverse careers. And that's where we think the AMS can help through internships, the mentoring program, and the student conferences. What other initiatives could the AMS be doing to help students and universities and employers in this environment where the traditional meteorology degree will not be enough anymore? So thank you for listening, and I'll hand it back over to Neil.
Thank you very much, Dave and Harold and Gary and Paul. Great presentation and always very thought-provoking. So we'll open it up for questions. So you'll see the Q&A box down there. So you can type in your questions for Dave and Harold and Gary and Paul. And I will definitely agree with a lot of what they said, with my many years in the National Weather Service, and with the whole ensemble approach. We do definitely need some machine learning to help us. We just had a storm recently here in Albany where the snowfall was actually outside the goalpost of the ensemble. So, and of course, machine learning can only learn from whatever the events are in the database. So, so let's see. So if anyone has any questions, again, please type in your questions in the Q&A box that you see at the bottom of your display. And let's see. So, so we have a question. If we were to change the BS degree requirements to include other areas, what would we remove from the present requirements? What would we remove? So that's the question. If anyone wants to answer that.
Yeah, this is Gary. We've just been having a curriculum discussion here in my department, and that comes up. I mean, it's a zero-sum game, and so, Brian, you're right. If we're going to add new requirements, we have to think about what to take out. And some of the old school physics and chemistry, everyone wants to hold on to the fundamentals, but we've talked about how much the students are getting out of those areas. So there may be opportunities, I think, revisiting some of those, the long laundry list that Harold showed there for the 1340. We want students that are eligible for those 1340 positions, but at the same time, we know that some of those classes are not really contributing to their preparation the way we would like.
Okay. So we have another sort of comment question. By the time OPM changes MET requirements and then universities redesign curriculum, the field will have already changed to something else. So these are things that are happening now. So should we be preparing 10 years out or more? I guess that's more of a comment than a question, but yeah, it does seem like it's kind of a moving target. So is there any more insight into how we can kind of stay ahead of the changes that we're sort of expecting?
This is Harold. I don't know if we can stay ahead, but I'm hoping we can at least move in a direction that we think that we're going to now. I mean, the disconnect right now between anytime you got a 30-year-old job description sitting out there with as much as has happened, I think we do know that there'll be some things one of the things is trying to figure out what those sort of, I think of as timeless characteristics we need. We need an ability to, to think broadly, to be able to be problem solvers, to understand the atmosphere, but also then now I think the biggest thing, and I don't think this is going to go away, is the ability to interact with users. And that's, I think, one of the biggest things that we don't have any of that description in our thing. And so I think that's one where we could go, but it's not an easy thing to do.
This is Paul Rover. I'd like to add on that. What Harold just said, I think, and the prior question, the only way that we really have the ability to get some additional pieces into the curriculum, so to speak, is to not have it be part of the formal curriculum, but be an add-on. And that's particularly true of these kind of professional development and soft skill kinds of things. So having some form of experiential learning like we do here at UW-Milwaukee has been really beneficial for our students, but it's not part of the formal curriculum because, as was noted, there really isn't any room in the curriculum to have something like that. And so we have to figure out ways to try to make this work, and that's the way we're doing it here.
Okay, well, thank you. So another question, what do the employment statistics show for recent grads, say roughly the past 5 years for Bachelor of Science grads in atmospheric science and meteorology? So what are there trends in the employment statistics for recent, fairly recent BS grads?
So this is Gary. I can say something about that. You know, we keep track for our graduate students with masters and PhD degrees. The placement percentage for the graduate students is almost 100%, a really large fraction. Almost all of those students get good jobs in the field. At the bachelor's level, you know, there's a lot more variety, and you know, we have people going in more different sectors and less into kind of the research. A certain fraction go into grad school, but you know, a certain fraction of the students just end up going into different fields outside of meteorology because it is a relatively small field, and I don't think there's enough entry-level positions. But you know, between the military sector, broadcasting, forecasting, educational sector, emergency management, there's lots of different opportunities, and especially in the private sector. I think it's for a student who's conscientious, there's still a pretty favorable job market, I think, overall.
Okay, so let's see here. So another question. So what would you suggest to forecasters that are, say, midway in their careers, 10 to 15 years or so, for continuing education to better prepare them for the latter half of their career? You know, any kind of studies of stats, probability, psychology, programming. You know, people in the latter half of the career certainly have to stay up to speed on everything also. So any suggestions?
Well, that's a good question, Gail. This is Dave speaking, and it really depends on the direction that the individual wants to go. Where do you see yourself fitting in? Where are the skills that you want to develop? And you know, I'm on a sabbatical this year, and I'm exploring a little bit of that myself, taking an R course, taking a Python course, because I feel that you know, just can't rely on GEMPAC anymore to, you know, create meteorological plots. And so for me, I'm using this time in part to upskill myself into programming and plotting.
And Harold, I would say that if you're a forecaster and you're, say, you know, with some National Meteorological Service, I think the biggest thing is trying to learn to understand either the human decision-making process, which maybe like a, you know, some sort of a psychology class or even a macroeconomics class would probably be a useful thing in there. If there's abilities to see decision, you know, decision sciences around, you know, things like that would probably be good. A lot of it's going to be reading a lot of books. I mean, I tell everybody they ought to read, who cares about decisions, ought to be reading Dan Kahneman's book, Thinking Fast and Slow. That's a really good resource for trying to understand how people in reality make decisions. The other thing I think to do is that we've had some people do this and this around here, is, you know, forecasters have to deal a lot with certain communities. So learning how, say, emergency managers do their jobs, taking all of those FEMA emergency management courses to get an idea of the constraints and the needs that community has is something I would also think of. So becoming a specialist with a really important user group would, I think, be a useful thing also.
Okay, we have a couple of questions that are sort of related, and it has to do with, are we graduating too many students with BS degrees? Should we be emphasizing, more of sort of a master's degree as a minimum requirement? And, including in the National Weather Service, there are more people graduating than jobs, and, the credentials may not be diverse enough for complex work. So should we be emphasizing more, going beyond the Bachelor of Science degree?
Well, I'll chime in. I think yes is, if a student wants to be competitive, having a master's degree where they pick up those additional marketable skills is really valuable. So sometimes we see students that graduate and they sort of test the waters with the job market, and they also apply for grad school. That's always something I recommend is, keeping your options open is putting you in a stronger position, but certainly getting more education and, and more marketable skills is going to help you. Even if you could get a job anyway, at some point it will probably help your upward mobility or your salary. And so there's a lot of professional advantages to getting a master's or a PhD, depending on what area of interest you have. And
okay,
okay.
Yeah, go ahead.
I was going to say, there are also these professional science masters where it's like a 1 year or 1.5 year program that has a very specific specialty. And we see those universities love those because a lot of times they can charge kind of a premium tuition, but that's another way of, it could be getting a GIS certificate or, some kind of emergency management certification. So there's things you can do where you can point to a specific credential that will give you unique qualifications for certain types of jobs. So sorry, Neil, to tack that on.
Oh no, yeah, I think your insights are very important, and I always respect your opinions and your research. So let's see. Well, I'm going to have to pick and choose a few questions because I'm glad that there's so many people with some good questions here. Let's see. It says that there's a lot out there for one degree program to anticipate. People need to know how to learn by branching out to other disciplines, but are there still the same headwinds disincentivizing multidisciplinary projects? Let's see. And how can schools facilitate these sort of things?
Yeah, I can answer that. This is Dave, and this is exactly what's happened with our school. We were originally a geology program, and then some changes to the university happened, and the atmospheric physicists came from the physics department, were thrown in there, and all of a sudden these people with very numerical strong backgrounds had to interact with people who were often a little bit shy from strong numerical and physical backgrounds, and so we've been evolving, and it's been a challenge, and in the meantime we've also added in a range of biologists and ecologists and archaeologists into our department. One of the reasons why we're so big, and so we just can't keep teaching an infinite number of these pathways. We have to step back and say, what are the broad skills that we offer, that we can offer to someone who's interested in earth and environmental science in the most general sense, and forcing this interdisciplinarity. I don't know about the US, but in the UK, the funding bodies are really pushing for this interdisciplinarity. They are having explicit calls for this, and that's driving us to think outside our departments and even outside the equivalent of what would be a college at an American university, and across the spectrum, and that's being encouraged. It's not easy, and not everyone will follow that lead, but there have to be people that have the passion, the desire to broaden what constitutes an education.
This is Paul Rober. I'd like to jump in on that too. From a institutional perspective, from the university perspective, it's very much built on the idea of silos, and it's very difficult just institutionally to cross those boundaries. And by silos, I mean specific departmental structures, or even sometimes within departments. You can try to do that, and as Dave was mentioning, it requires extra effort to actually get beyond that. I'd also say in the United States, although there's a lot of talk about multidisciplinary work, the actual funding mechanisms for that sort of work against that. It becomes much harder to get funded for something that's truly multidisciplinary than something that's more focused in one area. So I think there's a lot of value in that, but it's difficult to actually accomplish it. I'd also say that one of the ways that people, going back to some of the prior questions also, one of the things that people need to do is not just to look for formal programs, but as Harold mentioned, do a lot of reading and study on your own. Lifelong learning is a big part of this. It's just too much happening all at once to be able to expect that a single program is going to be able to give you everything you need.
Okay, so shifting gears a little bit, it says, can Dr. Rober or any of you expand a bit on the view of weather prediction to decision support? This element is critical in the future, requires a great deal of thought and attention to this evolution. If this evolution is ultimately to be successful, there's a strong association between competent scientific weather forecasting and effective communication and decision support. So the evolving role of humans in weather prediction and decision support.
This is Paul Rober again. I'll talk a bit about this from our experience here. So I have a program where our students actually provide professional weather forecasting for clients mostly in the private sector. And as I mentioned when I was talking before, these are groups of people who might be in the energy sector, for example, or something related to transportation. And they need to make decisions which are strongly dependent on what the weather conditions are looking to be over the next 24 hours typically. And so what our students do in that is, yes, provide the weather information, but the larger part of their work is actually just to communicate it in understandable and actionable terms for those users so that they know what they can do with this. And so it's not about a CYA kind of thing. It's about, okay, here's what is the most probable outcome, but here's also the most probable worst case outcome so that they can plan for those sort of contingencies. And that's a way of sort of translating probabilistic information into something that decision makers can actually understand and work with. So giving them sort of a red line of, this is the red line, and this is how close you are to it in terms of your decision, how it will be affected by that. And that again is something that as I mentioned before is not easy to give the students that kind of experience inside a formal classroom, and that's why we do it outside. We've done, the weather forecasting contests and things like that, and that gets you a certain way down that path, but it really doesn't get you to the communication aspect to the degree that really needs to happen. And so there have to be mechanisms for incorporating that into the training, either while at university, or if not there, then certainly when they're going into weather forecasting situations.
And this is Harold. I would add on to that when I talked about, for instance, in a weather service environment, when attempting to create expert teams, it may be the kind of thing that you have some people who are much, much better at that communication aspect and can take and you have people maybe perhaps who are better at identifying the weather side of it, and they work together to help communicate the information with that's necessary for the decision maker to use. So, and again, to come back to that thing about how people need to know enough about other areas to be at least conversant with them, but then also to take advantage of the specialist information and specialist knowledge that certain people might have.
Okay, so we've got another question that somebody who has a master's in computational math and statistics wanting to get into the meteorology into a meteorology career. So someone with a, again, math and stats background getting into a meteorology career. So how does somebody, get into meteorology beyond looking at just at AMS job boards to get into the meteorology field?
Well, in the federal sector, you're not going to be a meteorologist. I mean, you may be working in a meteorology area. We hire people as what we call physical scientists, or as engineers. They get into that. In the forecasting world in the U.S., in the public sector, that's extremely difficult. The private sector, it may be easier in some ways, in that people will have lots of needs for things. I know that in the years ago, in the 30 years ago now almost, the Canadian system took in people with a wide variety of undergraduate backgrounds, and then as part of the hiring process, they gave them a year's crash courses in meteorology, and then did I think a 9-month-long training course. And so they ended up with a diverse group of people inside that had perhaps backgrounds in physics and chemistry and computer science and math and meteorology as their undergraduates, and they had that blend. But we tend to, in the U.S., create, in our public sector, we tend to create a very, very homogeneous environment and kinds of workforce.
I would add to that those kinds of skills are definitely needed. So following up on some of Harold's suggestions would be a good thing, especially in a team kind of environment. So typically, I didn't mention this when I was talking about machine learning, but typically one of the elements that's critical to that is not just the technical skills, but also domain expertise. So you know what you're doing within that area. And so that's often not the case, that it's one person who has all of those things. So the teamwork aspect that Harold has been talking about would be very helpful in that kind of situation. So somebody bringing in the kind of skills that you're talking about, blended with people who have the meteorology background, could be very effective.
Okay, I guess I should ask if we have time for one more question. We're kind of at the top of the hour. If the AMS people, I guess, would let one more question, or I don't know if we have enough time, but okay, one more is okay. So I guess, has a future forecasting work environment been determined, and should training and education fit that environment?
No and yes. Yeah, I think that's one of the things, is that we don't really, at one level, we don't have a real vision of, especially for our operational forecasting sides, be it public sector or private sector. I don't think we really have a clear idea of what we're going to be doing in the future, and as a result, it's hard to design the training and education system to meet that. And I think that's a real struggle in trying to figure out what we should be doing in the future.
Okay, well, I would like to thank everyone who attended and participated. Thank you very much, Dave, Gary, Harold, Paul, and thank you very much. And please keep your eyes and ears out for the 4th webinar coming up in a couple of weeks, and for the panel discussions at the AMS meeting in Boston. Thank you, everyone.